will pick up the either position, or I will show you in the next slides, maybe force, maybe velocity, and information is captured. Now, in case of a servo mechanism, this transducer, the position transducer, is sometimes located within the actuator system itself. Okay? Within the actuator system itself. Okay? It can be outside also. In some cases, it will be within the system. So, if they say servo motor, servo electric motor, or AC servo, some servo electric motor, it will have a transducer coupled with its shaft. Okay, so when shaft is rotating, the transducer will pick up the position and will be able to give us the information as it is. Okay, so this is actuator position. Okay, assuming that all other outside parameters are known to us, right? Right, then whatever information we get when actuator is rotating, we can translate it into outcome, right? In terms of outcome, if it is other parameters are known. So in case of a servo mechanism, these transducers are placed within the motor system or actuator system. In case of some of the systems which may have external transducers. Okay, so in the previous floor, this is external transducer, okay, which captures the information and delivers the information to the controller, such as like this. In some cases, which I will show you after some slides, we will be able to see that the sensor system is not outside, but it is placed within the actuator position. Okay, so here valve, directional control valve is here, and this sensor will be placed within this, and the feedback is provided right from there. And as I told you, because if we put the sensor inside, it will provide quick and accurate measurements, not getting affected by any other parameters. Only thing is that we should know the mechanism and other translatory systems, right, very well. Then only we will be able to code, right, correlate both outcome. Right. And as I explained to you in the last class, in the last few minutes, last class, that it can be motor, we can control the motor, electric motor input itself, right, by driving the motor, and control the outcome at the far end hydraulic actuator. Or we can incorporate some type of variable pump system, variable speed, or connecting with the pump flow control valve, which will allow more fluid to just bypass or go out of the system, etc., and control the flow to this hydraulic actuators. This is another way. And the third way is to control the directional control valve itself. Okay, so it's not so efficient controlling of DC valve, because it will allow water to keep on actuating, right there, keep on driving the pump. But the thing is, it is although not efficient, but it is very fast and very easy to control, because the system is very small. Dynamic characteristics are far better as compared to the motor control. Okay. And so this type of directional control valve approach, controlling this is very easy, and it's being adopted in majority of the tracks. So how do we control directional control valve? We use like something different. See, if you see this valve, it looks similar, of course, 4x3 valve, but it has two parallel lines over here. Lines. So it is, we have learned in the last few weeks that, okay, 4x3 directional control valve, will work like this. We know. What I also told you that this outcome over here is either this or this or this, not anything intermediate. Okay, no. But if we convert this ball with some mechanism coupled with it, such a way that we can control the flow also at the same time, then two lines are drawn over here, and that is what is now controlled, right? It's a servo control. It is known as servo controlled directional control. Okay, it's a servo. What it means, I'll show you in the next slide. But however, there are three major outcomes that we generally look for in the mechatronic system. Is either a position control, position transducer will pick up the signal depending upon the output position, right? Output position, and that is being fed. Now, either you pick up from here, or within the transducer, within this control valve, there will be a sensor to pick up position, displacement basically, and this displacement and this displacement, there will be a difference of course. However, there is a relationship we know. So from this displacement, we will be able to derive this displacement as well, and we will be able to pick up this signal and use so. And in case of speed control, we will use, so in case of sensor control, we may use sensors. Of course, you may be knowing about it, but linear variable differential transformer, LVDT. Last bench, anything interesting? No, you were smiling, so that must be something interesting. Share it with us so that we also smile. No, you don't want to share it with us. Okay. So sensors can be linear variable differential transformer. It can be induction pickup. It can be strain gauge, right? So different types of position sensors are used to pick up that signal. Generally, in actuators such as like this, we use linear variable differential transformer. So what we have learned previously, sometimes, right, long back, right, maybe 100 years back, whatever.
Yes.
Try to decode. So that is position sensing over here. It can be a speed sensing using either a small electric motor type or generator type, right, or it can be based on either rotation, or it may be based on optical system coupled with encoders. Encoders, right, will help us to pick up the speed of rotation, right? You know optical encoders, you can learn incremental, absolute, or right. So those encoders also can be used for speed transducer, or it can be a load cell for force transducer. You know the load cell, right? We talked about strain gauges coupled with the in such a way that you can capture force or torque. Now, how this servo control valve looks like? So it has standard, the spool mechanism. Okay, so which is, if I position this spool, depending upon that, from pressure port the fluid will go to A, or from pressure port the fluid will go to B, or fluid will directly go to the tank L. Okay, is it okay? Depending upon the position of this spool. Now, what we have learned in our directional control valve, the position is controlled using a solenoid operation. So when we use a solenoid operation, although I am not deriving the relationship, I will just put it up in our practical it is something like something like this. In few millimeters, these dimensions are in terms of millimeters. The force, the driving force for this spool to be driven using solenoid operation decreases exponentially. It's not linear. So as the spool starts moving, the force acting on it will start decreasing because of the solenoid configuration. And hence, this is not a correct way to control, because we will have to always remember about position and corresponding change in the magnetic field to be applied to the solenoid, and indirectly current not to be applied, to be generated from the solenoid, and indirectly current to be passed. It will non-linearly change. So which is not a correct, very easy way. So here the operation is the one what I am trying to describe here is, let's say this is a transducer, linear variable differential transducer. When this core moves, the primary and the secondary coils will provide us the output. Right? If you remember LVDT, do you remember?
Yes.
No. Yes. 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 Very good. Can you come forward? No. No. All will say no. So you just to recall. It's I will not describe, but if you can recall. So this is a primary coil, these are secondary coils, and they are connected in out of phase 180 degrees, so as to give the output is the sum of these two coils. So when the core moves, depending upon the magnetic lines, flux of lines which are being cut, the voltage which is being the right induced right voltage will be captured. Okay, and position will give us this core position, right movement from the center will give us the outcome. So that is being captured by this transducer LVDT, right? So that is being captured by this transducer, and that output is being paid to the controller to provide the output here to the solenoid valve and change the current rating to position this. Is it okay?
So the position transducer.
So this is, let's say, spool moves. So accordingly this position will change. Accordingly the current required for applying generating the same force to move the will change. Is it okay? So this is was developed in 1980s. Okay, servo control valve by Vickers in Sweden. Okay, it's in 1980s, and today slightly different. Of course, this mechanism is also used by Vickers, and this is another mechanism which is described by it is a company named Moog has developed. I'll show you. This looks so complex, but simple for us. So this in this case, I want to control this spool position. Okay, fluid from P will go to either C1 or C2, and when P C2, the output from C1 will go to the reservoir or tank. Is it okay? I have copied from some other book where tank is represented by reservoir R. Okay? So this is the way it works. Now, in order to control this position, what we used to do? Operate using solenoid operation. Now here, it is not the solenoid operation, it is the fluid with the pressure P is used. Now this fluid comes here and it comes here. Okay, there is a nozzle located over here, and fluid also gets directed to this and this place. Okay, fluid with pressure P, both the sides pressure P are equal. So the over here, spool remains in a certain static condition, right? Okay, now these nozzles are open in front, and there is in front of them there is a flapper. Now this flapper is connected to a torque motor. So when the current over here changes, because of the corresponding north and south generation due to the direction of current and based on the amount of current, the magnetic strain, right, field which is generated will drive this motor flapper like this. Okay, so this one, right, which is something like a free core, will move depending upon the magnetic field strength over here. Okay, so this is S, this is N. So if current direction changes, this part becomes N, this becomes S. Automatically, this right part will move like this, and its position movement will depend upon amount of current which is. Accordingly, this flapper will move either right hand side or towards left hand side. Accordingly, now it will either block this or block this or partially block it, so that the resistance will change. Accordingly, the amount of fluid reaching over here will change. So pressure build-up will take place. Depending upon the pressure difference between these two, this spool will move in either direction. Okay, so this control, all this thing is directional, servo controlled directional control valve. Okay, and so one approach is, as I told you here, by controlling the solenoid current. Another approach is by controlling the torque motor current over here. Okay, so the torque motor, right, will change the armature position and accordingly flapper position, and flapper position will change here. So the pressure fluid which is coming here will change the position of this valve, and in turn this valve spool will decide how the fluid flow will be. Okay, so this mechanism is used to control the system, either pressure or right displacement. Okay, so this is much robust and linear control is possible with this, so which is being used, right? So basically, right, torque motor is controlled by the spool positioning and right inside this, and accordingly the output is H. Okay, so this is the way we use, right, directional control valve. So this is right nozzle, flapper, this is armature, this is a torque motor, and depending upon the current rating, this armature will tilt. Accordingly, this flapper will tilt toward this side or this side. Accordingly, the pressure differential from this liquid will build up, and accordingly, valve position is controlled. Okay, so this type of valves are known as proportional controlled, servo controlled valve, proportional Okay, it will control proportional right fluid or servo control valve in short. Okay, so this approaches are used. Now the amount of current which is to be controlled over here, it depends upon right position basically. Okay, and drive system, right microcontroller system will be able to drive this motor. It's a small motor. It will be able to drive this, or sometimes it needs little auxiliary, additional auxiliary power to drive this, right, by switching this right switches and control this drive. Okay, so in short, we started with our requirement is some hydraulic systems or pneumatic systems which can deliver the required output. So we started with conventional hydraulic systems, and directional control valve, if we convert it into right such a servo control valve, it allows flow control along with position. Okay, so the fluid which is going through this will have flow control also built in, automatically built in, depending upon the spool position. Okay, right, and at the same time directional. And why flow control is required? To reduce or to increase the speed, or when it goes to a particular position, to stop immediately. So accordingly, right, the control, flow control will not be there, automatically the position. Okay, so with this, right, the application is electrohydraulic motion platform. So what simulators they use? They all use such servo-controlled system. It is useful in missile launching, rocket launching, and automobile simulators, right, or helicopter means drive simulators, etc. They all use, because multiple such systems, hydraulic systems, and they have to be controlled positioning in all the 6 degrees, or depending upon required number of degrees of control can be used. Okay? And simplest application is here, right? This simple, right, single control is also possible. Okay? So the overall cylinder with the control valve with the cylinder will look like this, right? Although the mechanism inside is what we showed. Okay? So this is, so in summary,
So this is a directional control valve. The previous diagram was a directional control valve.
yeah, it's all with cylinders with a directional control valve. And so we talked about hydraulic systems. We talked about some components. We talked about circuits. We talked about loading, unloading, flow control, sequencing, high low pressure operations. I think I skipped it, but maybe in the next class, just I'll give you one very interesting application of circuit, and then servo, okay, systems. So from next Monday onwards, class onwards, we'll start with electrical actuators and try to see how they are being used for driving the systems. Is it okay? Do you have any question? Is it all right? It's fine. The content is fine. So one circuit I think I had skipped. I'll next class, before we go to electrical, I'll just describe that. It's very interesting application point of view and maybe practical, right, requirements point of view. So we'll try to see those things. Thank you.